take a simple example to show what exactly we are trying to do over here. Let's just take two dimensions. Okay, let's work with a yeah, let's work with a query that has, you can turn off the microphone. Yeah. Let's work with a query which has the word gossip and the word jealous in it. So there are only two terms in the vocabulary. Okay, gossip, jealous. And we have a query that has both these terms. We have a document D1 that has gossip in it. Okay, but it doesn't have well, strictly speaking, it it does have the word jealous in it, but let's say gossip appears uh, I don't know, n times and jealous appears just once. Okay, so if you plot um, the vector for this document, it's going to appear close to the y-axis here because the gossip axis, because it has only the word gossip in it, approximately. And likewise, you have a document D3 which has the word jealous in it, but not gossip. So D1 has gossip but not jealous, D3 has jealous but not gossip. And then you have D2 which has gossip and jealous, but both appearing multiple times. Okay, so if we don't convert these vectors into unit vectors, then the vectors are going to look something like this. Okay, D2 is going to extend far out into this 2D space. D1 and D3 will be here, and you have the query here. So you can see from this example, I mean, we've already seen why using the example of these two documents D and D prime, why Euclidean distance wouldn't work. In a similar way, you can see that it won't work here as well, because the query has both these terms. This document has both of these terms, but if you look at the Euclidean distance between the query and the second document, it's more than the distance between the Q and D3 and Q and D1. Okay, even though both D1 and D3 have just one of the two query terms, whereas D2 has both the query terms, still the distance between Q and D2 is longer. And that's because we have not normalized these vectors. The normalization is important. Uh, Once we normalize, then D2 is going to come somewhere over here. So it will be close to Q. Okay, and so we can calculate the angle between the two vectors. Actually, so there are two ways to think about this. One is to first do the normalization and then compute the dot product. Another way to think about this is to not do the normalization, but then use the formula cos of theta is a dot b divided by the magnitude of a and the magnitude of b, right? And it's the same thing. The cosine between the query vector and the document vector is the dot product of, sorry, cosine of the angle theta between the query vector and the document vector is the dot product between the query and the document divided by the magnitude of the query vector and the magnitude of the document vector. Okay, so we can take this magnitude and combine it with this vector, and that will become the unit vector in the direction of Q. Likewise, this vector d divided by the magnitude of d is just the unit vector in the direction of d. Right, so you could either do the normalization, or you could first take the dot product and then divide that dot product by the product of the magnitudes. It doesn't matter which way you do it. But in either case, you will be measuring the angle between the two vectors, or more specifically the cosine of the angle. And if you do that, then you can see that D2 will appear somewhere over here. So the angle between Q and D2, or even if you're directly measuring the angle without normalization, the angle between Q and D2 is very small. Whereas the angle between Q and D1 and the angle between Q and D3 is large. That means Q and D2 are closer to one another, then Q is closer to D1 or D3. Right? D2 is the most relevant document here. So do you get the idea of what exactly we are trying to do when we compute these cosine scores? I mean, visually, that what we are trying to do is bring. So if you plot these unit vectors in this v-dimensional space, so imagine a unit circle. Okay, imagine a unit circle over here. All these vectors will have their endpoints along this unit circle because this is the circle whose uh, I mean any vector of length 1 will be like a radius, one of the radii of this circle. Okay, likewise in this v-dimensional space, imagine a v-dimensional sphere, if there is such a thing, in the first quadrant, and all the vectors, the query vectors and the document vectors after normalization will be points on this v-dimensional sphere or the v-dimensional surface. Okay. So this is something I just showed you. The cosine of the angle between the two vectors. If the two vectors are already expressed as unit vectors, we just take their dot product. Okay, so if Q and D have already been length normalized, then the cosine of the angle between them is just their dot product, and their dot product is nothing but the product of their components added together, component by component. Take the product component by component and add it. And if they are not normalized, then you take their actual dot product and then divide it by the product of the magnitudes of the two vectors. Okay, and again remember that these vectors Q and D are vectors of TF-IDF weights. Okay, so the ith component of vector Q is the TF-IDF weight of the ith term in the vocabulary, and that is being multiplied with the TF-IDF weight of the ith term in the vocabulary, but the TF-IDF weight in the document. It is the TF-IDF weight in the document for the ith term in the vocabulary. Okay, so this is what I mentioned, that if you convert them into unit vectors, you'll have a unit circle and then all the vectors lying along this unit circle, or in general along this v-dimensional surface. Okay, so let's take an example. Um, we have these three classical novels: Sense and Sensibility, Pride and Prejudice, and Wuthering Heights. And let's focus our attention on four random terms in that. Well, maybe they're not exactly random, but they've been chosen nonetheless. These are the four terms: uh, affection, jealous, gossip, and wuthering. In Sense and Sensibility, the term frequencies of these four terms are given in this column. In Pride and Prejudice, the term frequencies are given in this column. And for Wuthering Heights, the term frequencies are given in the third column. Okay, so these are three documents. And because there are four terms, if we represent these four documents in four-dimensional space, we will get 3 points for these three documents. So let's do some calculations. Let's represent these documents as vectors of TF-IDF weights. Okay, that's what we first need to do in order to try to represent them in four-dimensional space. So for these term frequencies, what would be the TF-IDF scores? So let's compute the TF score, let's compute the IDF score, and then multiply the two. So what would be, so let's work with log frequency weighting now for the TF score. Okay, what would be the log frequency weighting of weight of this particular term, 1 plus log of 115. Okay, and log of 115 to the base 10 is slightly more than 2, and so the TF score for this particular term is going to be slightly more than 3. This is the value. Similarly, the TF score for this particular term is 1 plus log of 10 to the base 10, which is 2. Okay, 1 plus log of 10 is 2. The TF score for this would be 1 plus log of 2, which would be 1.3. And because this term does not appear, because this term does not appear in the document, the TF score is going to be 0. We can do the same calculations to calculate the TF scores for uh, this particular set of terms, so basically the IDF score here is assumed to be 1. Okay, so again, the calculations that have been shown in this slide are assuming a simplified scoring scheme where the IDF score for every term is 1, and so effectively the TF IDF score is nothing but just the TF score. Okay, and so if you convert from these three columns, you can compute what the TF-IDF weights or the TF-IDF vectors will be for the 4 documents. Now these two values are 0 because this term does not appear in these two documents, but it appears in this particular document. And similarly, gossip does not appear in this document, and so the score is 0. Now, if we want to compute how close these points are to one another in v-dimensional space, we'll have to do length normalization also. Okay, of course we could directly compute the angles between the three vectors, but let's just assume that we are going to first do length normalization before taking the cosine scores. So how do we normalize this vector? This vector has 4 components. So the normalized vector will have components 3.06 divided. The first component of the normalized vector will be 3.06 divided by the sum of the squares of 3.06, 2 squared plus 1.3 squared plus 0 squared. Okay, this will be the first component. The second component, so that's what this value is. The second component will be 2 divided by this same denominator, which is this value. The third component is going to be 1.3 divided by the same denominator, which is this value. And the fourth value will be 0, because if the numerator is 0, then this fraction will also be 0. Now you can actually verify that these are unit length vectors. We are doing the same thing for this vector as well as for this vector. We are normalizing all 3 vectors. You can verify that the sum of the squares of 0.789 plus 0.515 plus 0.335 plus 0 squared, the magnitude of this vector is something you can verify is going to be 1. Okay, so we have these 3 vectors in 4-dimensional space. Now let's compute the cosine score between these 2 novels, Sense and Sensibility and Pride and Prejudice. If you look at the cosine score will be just given by the dot product of these 2 vectors, because they've already been normalized. So we don't have that, the product of their magnitudes in the denominator. So it's just a simple dot product, and the value we get is 0.94 between these 2 novels. If we compute the cosine score between Sense and Sensibility and Wuthering Heights, we get a score of 0.79. And if we compute the score between Pride and Prejudice and Wuthering Heights, we get a score of 0.69. So what does this mean? Okay, so how do we interpret this cosine score? Well, we have the cosine score between Sense and Sensibility and Pride and Prejudice to be quite high. It's around 0.94. It's higher than the other two cosine scores. So can somebody explain what this implies? What does this mean? Okay, you have three novels. Two of them have a very high cosine score compared to, the cosine score between the, either of them with the third. Firstly, which are the two documents that are closest to one another among these three? Are all of them equidistant from one another, or are two of them closer to one another than the third? Anybody wants to answer this?
So, hello.
Yeah.
Sir, is D2 and D3 I think are the closest.
Sorry, I couldn't hear you properly.
Can you hear me now, sir? Hello, sir.
Yeah, I can hear you.
Okay, the documents I think the D2 and D3 are closer to each other.
Your voice is loud, but it's very muffled. So
So, can you hear me now?
it's slightly better. Yeah.
Okay, the documents D2 and D3 I think are closer to each other.
So which are the two novels closer to each other?
SAS and PAP because as you said, the action value is great, proximity will
Sorry,
be great.
it's still your voice is still not audible. Mhm. Hello.
Can you hear me now, sir? Sir, can you hear me now, sir? So, is it right now?
Actually, it's still like it was before.
Yeah.
Um, Maybe can you like increase the distance between yourself and the microphone and then speak the same way?
Is it audible now, sir?
Yeah, yeah. Now it's fine.
Okay. As you said, the cosine, like the greater the cosine value, like the greater will be the proximity. So I think SAS and PAP, it'll be very easy to find. They'll be present in the document. And you asked like one more question, which are the two documents that are closer to each other? So I think it is D2 and D3.
So so let's just work with these names. Which are the two documents that are closest among these three?
SAS and PAP.
Okay. Yeah. Now, why do you think these two are closer than the third? I mean, think in terms of what the documents themselves are.
Yeah, because the cosine value which we calculated, it's saying 0.94, so
Yeah, yeah.
it's greater than.
So mathematically, that's true. I mean, the cosine value is the highest for this pair of scores for this pair of documents, and so these two documents are closer. So if SAS will be something like this, PAP will be something like this, and then WH will be far away compared to these two. Now, why do you get this kind of pattern? Why are these two documents close? What does this tell you about the two documents? I'm not asking mathematically, but in terms of your English reading, is there anything about these two documents that could explain why you're getting scores like this?
So is it because they have the same author?
Yeah, it's because both of them have the same author. Jane Austen has authored both of these, and who has authored Wuthering Heights?
Thomas Hardy.
It's Emily Bront. But Thomas Hardy is actually one of my favorite authors. So uh, I wish they had chosen some other document here. I like tragedies. Okay, so Jane Austen has authored these two books, and if the same author is authoring, multiple books, the tendency will be to use the same kind of vocabulary, right? Generally, I mean, maybe some authors can artificially adopt a different style, but assuming that the author is adopting the same style, uh, you're going to find similar proportions of words used in the works. Okay, so this word, for example, wuthering, is not used by Jane Austen anywhere. Okay, and you can see that probably in your own life as well. There may be certain you know English terms that you never tend to use, but somebody else may be using those terms pretty frequently. Okay, so when the reason for you can turn off the microphone now. This has further applications also. I mean, people have been using this kind of uh, analysis, for clustering together documents that are similar. Because many times what happens is, if we go back to more ancient works, works like, for example, the Bible, or Homer's Iliad and Odyssey, or the ancient texts from India, Mahabharata and all. Of course, Mahabharata is in Sanskrit, and these other works are in Greek and Aramaic and all. But if you were to imagine doing this kind of an analysis in those languages, you can often detect when that whether or not that work was authored by the same person or not, right? Because you could take different sections of that work, which have been preserved as one work, but may not necessarily have been authored by one single person. So styles can often vary. If there are multiple authors that have authored a single, what has come to be a single work, then the styles between different sections of that text will vary. And this kind of an analysis, in a more sophisticated way, can reveal uh, can often reveal when a single work, whether or not a single work really had a single author or not, or whether there were multiple authors behind it. Anyway, so I don't want to get distracted by that example, but um, it's an interesting application of the cosine similarity score, because these are mathematical formulas, but if you think about how you could apply this for clustering together documents, and what implications that has on detecting multiple authorships, or if you have anonymous works, sometimes anonymous works are attributed to a popular author, um, and that's also something you can detect using these kind of techniques.